Welcome back to SanfordFlipMath. This is AP Calculus. We are again moving along through the derivative chapter in specifically the book we're using is Finney, Demana, Waits, Kennedy, 3rd edition, the book that is a calculus book, and we are going to focus on chain rule today. And let me start by giving you a reason to do it. Okay, so first of all, if I was going to look for if I wanted the derivative of this f of x, I already know how to do that. I can just come in here and the issue is right now I'd have to multiply this out. So 3x minus 4 times 3x minus 4, and this is not a big deal. This is a little algebra 1, so 9x squared minus 24x plus 16. And again, this is still f of x. I've not done a derivative yet. And then f prime of x. So using the power rule, 2 times 9 is 18. Subtract 1 from the exponent, x to the 1. Minus 1 times 24 is 24, x to the 0. Derivative of the constant is 0, and so that's the derivative. So not that big of a deal to do the derivative of this. We could use a power rule also, and this would be the u, this would be the v. We'd be doing v prime times u, and u prime times v. And again, I mean, it's kind of overkill for this problem, but it would be fine. Okay, so let's take that same problem and turn it up a notch. What if I'm doing f of x equals 3x minus 4 to the 7th? So 3x minus 4 times 3, okay, so I need to multiply a lot of factors of 3x minus 4, and can I just say that this is going to get old? I'm not even done. I'm not even there yet. All right, so this would get old in a big time hurry. So let's just say I'm not going to do it. Okay. So the thought is there is something called the chain rule, and this looks like a lot of stuff. Okay. So let's first start out by not looking at this. Okay, and I'll just go ahead and get rid of that for now, and we'll just come back to it some other time. Okay. All right. So look at this. There is some function f of x, and it's like an outer function. It's the outside. And then there's this other function on the inside. So the idea is you have a function inside another function. They're nested. One is inside the other. Okay. If you want to know the derivative of that, if you have some function like that, then you can do the derivative. And what you do is kind of do the derivative of the outside. And you keep the inside just like it is. And then you're going to multiply the derivative of the inside times that answer. Okay, so here is that derivative of that function on the outside. Keep the inside, and I know this looks all complicated, and it's really not that bad, times the derivative of that inside. Okay, so here's some notation. If I'm talking about some function that's f of u of x, then if I want df dx, I basically I'm going to do the derivative of that function with respect to u times the derivative of u with respect to x. Okay, and so I got like 7 different notations going here, and I'm not trying to confuse the issue, but the basic idea is the derivative of the outside times the derivative of the with the inside still in there times the derivative of the inside. All right, let's do an example. It sounds worse than it is. Okay, come back to this page and let's go back down here. Okay, so I'm going to look at this. I'm going to pretend that this is some other function, like that's a function of u, and it's u to the 7th. So think about how would you do the derivative if it was just about u. So it'd be 7 times u, and then 7 minus 1 is 6, so 7 times u to the 6th. So that's how I'm going to do this derivative. Okay, so here's f prime. I'm going to do 7 times 3x minus 4 to the 6th. Now the only catch is it really wasn't, it really wasn't a derivative. I haven't done a derivative with respect to x. I've done a derivative with respect to 3x minus 4. Okay, so what I just did was dy du. And if I want to do now the derivative of dy dx, I have to multiply by the derivative of the inside. Well, the derivative of 3x minus 4 is 3. That's the derivative of the inside with respect to x. And notation-wise, this is dy dx, which is what I wanted, and here it is. Now, normally, we would write that, okay, 21, 3x minus 4 to the 6th, and we are done. Okay, so it's the derivative of the outside. In this case, we use the power rule with respect to, and then you just keep the inside like it is, times derivative of the inside. Okay. This appears in the big list right here. And again, the idea is dy dx equals dy du times du dx, and the u is the inside. Okay. So again, if we're going to have this in words, we'd say derivative of the outside times the derivative of the inside. Okay, and I mean that's a very simplified way to look at it, but I'm telling you that's basically what works. Okay, let's do another one that's a power rule. Okay, so let's do 5x minus 7 to the 5th. Okay, so y prime, we're just going to do the power rule on the outside. Okay, so it's going to be 5 times 5x minus 7 to the 4th. Just like I normally do power rules, it's just we're used to this whole thing just being x. Okay, well, and then times the derivative of the inside, where the derivative of the inside is just 5. So this becomes 25, 5x minus 7 to the 4th. Okay, let's do another example exactly like that one, only completely different. Let's do the derivative of, oh, I just scared a whole bunch of people, sorry, x squared plus 4x. Now remember that roots can be written as fractional exponents. So I'm going to rewrite this, y equals x squared plus 4x to the 1/2 power. Okay, now I haven't done the derivative yet. Okay, so y prime equals 1/2 x squared plus 4x. And now I have to subtract 1 from the exponent. Okay, why is that set of parentheses there? Because I need to do the derivative of the inside. Now the inside's a little more ugly this time. It's less fun. So 2 times, so I got to multiply. So this is 2x to the 1 plus the derivative of 4x is 4. And that's pretty much done. The only thing that we could do with this, and again, in terms of AP, if this was a free response question, you could be done. I'm going to go ahead and do, I can't distribute 1/2 across this because I have this lovely exponent here. But I do have some multiples of 2 here that I can divide out. So 1/2 times 2x is going to be x. 1/2 times 4 is 2. And so this then becomes x squared plus 4x to the negative 1/2. And again, so this is fine. Just one more way that your book would probably leave this x plus 2 over the square root of. Okay, and you ask yourself, why did he just put that in the denominator? And why is it a square root? Okay, let's do another. Y equals 5 times the sine of 2x. Okay, we just learned about trig rules yesterday. So this is going to be 5 times, well, the derivative of sine is cosine of 2x. Remember, you keep the inside the same. Okay, it just comes along for the ride, but then times the derivative of the inside. Okay, so, sorry, that's y prime. So y prime then is 10 times the cosine of 2x. Parentheses there are optional. What about y equals cosine squared x? Okay, now here we need to kind of be thinking cosine squared, what's the inside function and what's the outside function? Now, at some point here, you're not going to need to rewrite it like I am right now, but I want to make it very, very obvious that this is the cosine x squared. That's really what this means. So if that's what this means, then for me to do derivative, the outside function is really squared. Okay, so this becomes 2 times, keep the inside the same, to the 1. Again, you don't really need to write that. And then the derivative of the inside, derivative of cosine, is negative sine. So again, if I were going to make this a little nicer form, this becomes negative 2 cosine sine. And I don't know of any, no, all right, well, if you were feeling especially spunky here, I'm just going to rewrite this one more. Now, again, and some of you are just going to freak out when I do this, but sorry. So this is fine. This is fine. 2 sine cosine, if you recall, all right, don't all hate me, is the same thing as sine 2a, in this case sine 2x. So this is another way to write this. So this is back from chapter 5 in our pre-calc book from last year. Sine of 2a equal to sine a cosine a. So if you happen to remember that, that's this with a negative sign out in front. So I just brought the negative along, a factor of negative 1. Okay, well let's do a little bit more with this. Let's say we have y equals sine of x. What I'd like to do is we're going to find y prime and we're going to find y double prime. In other words, the first and second derivative. All right, well the first derivative of sine is cosine. The second derivative of sine, in other words, the derivative of cosine, is negative sine. Well, that's not terribly exciting. Why didn't you just have that in the work from yesterday? Well, I could have. What makes this a little more exciting is what if I do the tangent of x? Well, the derivative of tangent is not cotangent. The derivative of tangent is secant squared of x. Now, to do the derivative of secant squared, this is now a chain rule problem because really that's the derivative of secant squared. Okay, so here we go. Derivative, so I'm going to do 2 times, so this is 2 times the secant of x to the 1 times, now I need to do the derivative of the inside. Well, the derivative of the inside, derivative of secant is secant tangent. Okay, so this is the second derivative. A little more interesting this time. Okay, and again, we're remembering all these crazy rules. Okay, so just for those watching at home, if you wanted to clean this up a little bit, we could call this secant squared tangent. Okay, and again, I'm fine with either of those, just so you're aware. Okay, so, okay. All right, well, since we're making this a little more exciting, let's do, now this one I'm going to borrow from your book, and this is number 20 from page 153. Y equals x over the square root of 1 plus x squared. All right, now Mr. Sanford, now you're just being mean just to be mean. Yeah, I suppose. Well, how do you start this? Okay, this is a quotient, so this is u, this is v. Okay, so remember the quotient rule starts out the v, the denominator, times the derivative of the numerator, so we'll do the numerator in blue. Derivative of the numerator then is 1, okay, minus the numerator times the derivative of the denominator. All right, so I'm going to buzz over here for just a second to do the derivative of the denominator. Here's v. Okay, not a negative 1/2 because I'm pulling the denominator separate. Okay, so v prime Okay, so quick little recap here. When I did the power rule, I'm multiplying by the exponent, and I'm taking the exponent down by 1. 1/2 minus 1 is negative 1/2. Derivative of the inside, because there's a function inside of a function here, is the 2x. Okay, well that is just a lot of fun. I would recommend doing just a little bit of simplifying here. Okay, and so again, v times u prime minus u times v prime. All right, here comes v prime. It's going to be x times 1 plus x squared to the negative 1/2. And again, the denominator squared. Okay, not a lot going to happen with this in terms of simplifying. I'm going to do a little bit of simplifying here. All right, I guess I'll do a little more. Square root of 1 plus x squared minus x squared times 1 plus x squared. And when I square this square root, okay, just for the record, I'm fine back here. I'm digging this quite a bit. And then some of you I know are going to want to be able to check stuff in the back of the book, and this is not so pretty. You know, this is probably not what the back of the book's going to have. I don't know. I didn't look, but I'm guessing. All right, well, how to make this look nicer? I don't know. This is like one of those things that at some point you just have to make a judgment call. And you know what? I'm just done with it. It's not worth continuing fighting with this. Okay. All right, I need to talk about an alternate version of the chain rule. What we've talked about so far is the idea that if I do dy du times du dx, I get dy dx. Okay, basically notationally this is what it looks like, but in terms of what's really happening with calculus, it's a little more complicated than that, but that's the idea. Okay, I need to talk about this. Oops, sorry, not dy on the bottom. Okay, so the idea here is that this is the same thing as dy dt times the reciprocal of dx dt, so dt dx is dy dx. So this is another form of the chain rule that basically says if I have, this is like looking at velocity in the y direction, and this is looking at velocity in the x direction. And if I want to know the velocity of y with respect to x, in other words, change in y over change in x, then I can put them in a ratio and I'm good. It's like the time stuff just kind of goes away. Okay, this is based on the idea that we would have a function of x and a function x of t and a function y of t separately. So like let's say I had something like 30t for x, and let's say I have negative 16t squared for y. Now here's the idea. This is like physics. This is a horizontal equation. This is the vertical equation, and these are called parametric, and don't believe we did this in pre-calc last year. We just didn't have time to do everything. Parametric equations are equations that are both written in terms of some third variable called a parameter. And the most common parameter is t. Right, so the idea then is this is all about the vertical stuff, and then this one's all about the horizontal stuff. And what if I want to know what the change in y with respect to x is instead of the change in y with respect to time? So it's kind of like a speed, it's a velocity, it's a rate of change, but it's not with respect to time this time. Okay? Well, I could take this equation, solve it for t, so like t equals x over 30, put that in for t here, and I could do y of x, y as a function of x, is negative 16 x over 30 squared. And then I could just do derivative. That's one approach, and it's a good approach. It's a fine approach. The other option is do dy dt, which is negative 32t, over dx dt, which is 30. And if I do that ratio, this becomes negative 32. So this is now dy dx, which is negative 30. Oh, got a bell coming. Sorry, I got to get that out of the way. Close. Thank you. All right, let me just finish this up. 32t, switch markers in the middle. Nice job. Which you can then reduce. Nice. And if you rewrote t in terms of x, then you'd be all set. All right, that's one example of parametric. I'm going to leave it at that. 21 minutes. Write it down. Not bad. Talk to you later.